PhD in the University of St. Petersburg in 1999, after which she spent postdoctoral stints in Missouri, in the University of Missouri in Columbia, in Norwegian University of Science and Technology, and she held a short-time visiting position at the University of California, Davis, before moving as an associate professor to NTNU, where she stayed until 2018. Then she spent 2 academic years at the Institute of Advanced Studies in Princeton as a von Neumann Fellow, after which she moved to Stanford University, where she is now. Eugenia works in harmonic analysis, PDE, potential theory, and related topics. And her research has been recognized in several ways. Maybe most notably, she got the Clay Research Award in 2017, joined with Alexander Logunov for the development of tools that led to the solution of Gauss and Navier-Ashvili conjectures. She was a speaker at the International Congress of Mathematics in 2018 in Rio de Janeiro. And she's a member of the Norwegian Academy of Science since 2018 and a fellow of the American Mathematical Society since this year, 2024. Her talk today has the title Phase-Space Localization of Eigenfunctions of Schrodinger operators. Eugenia?
Thank you very much for the invitation and for the introduction. It's a great pleasure to be here. I think it's my first mathematical visit to Madrid ever, and it's nice to be here. It's very short, but so we'll talk about phase-space localization of eigenfunctions of Schrodinger operator, and it's a joint ongoing work with Svetlana, my brother, and Jaume Didius from ETH in Zurich. It's ongoing work. I will give you some results. I will formulate more questions than answers, and all mistakes of the talk are mine, not of the microoperators. Let me describe the problem and tell you what we're talking about and why it's actually a problem in harmonic analysis. Yeah. So we'll think about classical Schrodinger operator in Rn. Most of my talk I'll think about positive potential. Potential is always real valued, it's of a joint operator. And if you don't want to think what happens at the infinity, you can always cut it and take a periodic operator on top. I'm not going to talk much about what is the behavior at the infinity, just think about potential that will grow at some point or cut a large interval, and everything should depend on the length of the signal. If you think about a classical particle with this energy, you have kinetic and potential energy is positive, so the particle will be classically in this allowed region where the potential energy is less than the energy of the particle. So we have this reasonable set in the physical space where most of the quantum particle wants to concentrate. It's allowed region. So this is part of the space where the potential is less than, and there is a part where it's larger than E. There is some set where it's equal to E, but it will not be important in my talk today. So it's well known that in the forbidden region, the eigenfunctions decay exponentially. And it's a very nice result of Schmoller-Gmund from, I believe, 1980s, where he introduced the distance. When you're in the forbidden region, you take 2 points, take the function that is potential minus your energy, where it's positive, square root of it, and integrate. So for each curve, you now define the length of the curve in this way. When you're staying in the allowed region, this is just 0 because V is less than E. You're integrating 0, all those. You travel for free in the allowed region. But if you want to go to the forbidden region, there is a price to pay. And this is the way. And this important and nice theorem of Agmund says that if you have an eigenfunction, now use an eigenfunction with eigenvalue E, energy level E, then it decays in the forbidden region in this way. So there is some constant depending on the function, but then you have exponential decay with the function in the exponential up to small constant, that is this Agmund distance. So in the physical space, we understand what happens to eigenfunctions quite nicely. And before I'm going to formulate what our problem is, I will describe three other results that are connected to it and that were inspiration for our work. The first one is so-called Zickel-Lieb present-bloom inequality, and we think about positive potential for some technical reasons. Here the dimension is at least 3, and you want to count the number of eigenvalues with multiplicities at the energy less than E. You have a positive operator for positive D, so all eigenvalues are positive. You want to count how many of them are below this level. And they're saying, using Sobolev inequality, it's not very difficult thing to do. I forgot the parenthesis here, but you understand. What you are doing, you look at this allowed region, and you construct a region that is allowed in the phase space. So you add the momentum and look at all points for which the sum of the potential energy plus kinetic energy is bounded by E. You get this allowed region in the phase space. And they're saying that the number of these eigenvalues is bounded by the volume of this region. It's a very nice estimate. There is some constant there depending on the dimension. And it's how it should be because you believe that these quantum particles want to concentrate in the allowed region not only in the physical space but in the phase space as well. However, this inequality is one-sided. There is no way controlling this volume to control the number of eigenvalues. There are examples where this volume is large, but the number of eigenvalues is small. And you can easily see what the problem is computing the volume. We have uncertainty principle. If this volume consists of very thin droplets in the phase space, there is no way to put your eigenfunction there. So there was a very nice work of Charlie Pfefferman, who wrote a very long article on it. With very many beautiful things there. And one thing is simple, what I'm going to talk about in this slide is a simple part of this article that is called Uncertainty Principle. He is saying, yes, counting the volume is not the right thing to do. What you should do is look at the phase, first look at the physical space, cut the physical space into boxes. What is the size of the box? You want to construct an uncertainty box in the phase space, and you want in this box the kinetic energy to be bounded by E. It tells you that you want this size to be like square root of E. So you are choosing partition of your phase, for your physical space into boxes of size 1 over square root of E. If you will choose smaller intervals and you will do the uncertainty boxes, the kinetic energy will be large there in parts of this box. So if you want to do the right boxes, also you don't distinguish. If you do the very, very large, then the kinetic energy is too small. So do those so that the kinetic energy is of order E, and look what is the potential energy in this box. For this part of his work, he is saying, let us not think too much about what kind of potentials we will have. Think that this is polynomial of bounded degree. And basically how he uses this is that all the norms are equivalent. You want a function for which you can compare different norms in a cube. And then I'm counting the number of cubes where some norm is bounded by E. You can take the maximum, you can take the average. The average will be potential energy of a bump in this box will be like some norm of the potential. So after you do this, count the boxes where the potential energy is less than E, and then you have the count. The number of eigenvalues less than E is bounded from above and below by the number of such boxes, but the price that you are paying is that there are two constants here. There are two multiplicative constants. For the small energy, his procedure is nice for many potentials, and you can try to locate the first eigenvalue. But when energy is larger, you have this multiplicative error that we don't like very much. So part of what we're trying to do is to get rid of this error here. There is no way to make those two constants close in such arguments because you try to cover, you have some difference between bump function and the square, you have multiplicity, and there is some geometric constant that will appear in this way. So in a sense, one of the aims of what we're trying to do is to make the ratio of those constants close to 1 and introducing a count for this problem. Yes, I also want to say that there was a work by Rubio Shen in the end of 90s where he extended the results of Pfefferman to a larger class of potentials, and still good potentials when you have doubling inequality for the potential and some kind of Schrodinger inequality of potential. And still this works. The argument can be extended to some larger class of the potentials. There is a second result of Pfefferman that is very nice, and it's harmonic analysis, and it's one of the interesting applications where he is saying, now let us change the point of view, and instead of bounding potential from below, bound the potential from above. I mean, we're thinking about different energy levels. If your potential is bounded, you can always shift it. But think about potential that's bounded from above and try to count how many negative eigenvalues we have. There is a positive part that corresponding to the kinetic part. Now the potential gives you some negative part of your operator, and you want to bound how many eigenfunctions are there. And there are two estimates. One is saying if you can find many cubes where the potential energy in each cube is larger than the kinetic energy in this cube, then you have an estimate for your number of negative eigenvalues from below. Those cubes should be disjoint, but also their double should be disjoint. And this is an easy part of the argument. Basically, you have places where you know that if you put bumps, those bumps are clearly linearly independent, and the energy of the bump is negative. It's what this is saying, that the potential is winning against the kinetic term, so the sum of the energies, now the potential energy is negative, this is negative. Those are not eigenfunctions, but minimax property will give you very, very clearly that then the number of eigenfunctions is at least this one. So this is an easy problem.
But, so in the first one, what has to do capital N with L? L.
Sorry, this should be L. Yeah, thank you. This is L. You find L cubes, and then you know that this number of negative eigenvalues at least L. Yeah, thank you. Sorry for that. But the nice thing is that with this procedure, you can, up to this multiplicative error, you can bound the number of negative eigenvalues from above as well. If you know that you have an integer that is smaller than some small constant times the number of negative eigenvalues. This is n of 0 now. Then you can find L disjoint cubes where not the potential energy, but some mean of your potential is larger than that. In particular, if you think about V being not only negative, but in some nice class where the norms are comparable when you have the reverse folder, then you have the same kind of estimate, but with another constant. But the beauty of this result is that you don't need anything from this negative potential. You can work with any negative potential, and you have those two results. We're going to work with positive potentials, but this idea that you should take cubes where the energy, potential energy and kinetic energy match is important. So this will need a bit different way, but it works. And it comes from this work of there is another way to count this integrated density of state, and it is based on the tool that was introduced by Losch and Berde around 10 years ago. That said that you have your Schrodinger operator. In this case, we assume that the potential is non-negative, and you construct a solution to the equation HU equals 1. You construct this one function that they call landscape function, and it has many properties of the function. So 1 over u is a smoothed version of the potential. This is a nice identity that basically tells you that you can rewrite your operator in different terms to get from bad potential V to a nice potential 1 over u, use solution of some elliptic PDEs. It has some regularity properties. The price that you are paying is that now your energy is not very nice kinetic energy, but you have this very kinetic energy. Okay. And this is what they also call the effective potential. And it's a smoothing of B, roughly speaking, on the right scale. So this landscape function coming from this equation knows how to take the average, which is the right scale to take the average of B. It will depend on the position in the space. And in these terms, the count of the integrated density of states is like that. So you, once again, do as Schifferman in his positive part of the work. There should be union. You take RD, cut it into equal cubes with side lengths of the cube of this size, 1 over root of E, and you count the cubes where the potential energy, or with this new potential, is less than the kinetic. And then if you have some additional condition on regularity of the equation that is can be rephrased in terms of the regularity of U, we have this inequality. They have another result where you don't ask for this condition, but then there is a narrow term from the estimate from below for the number of negative. So sorry, for the number of eigenvalues less than. So this is another type of this estimate. Looks like there are many potentials for which you can do that, and very recently, like a couple of months ago, there is a preprint by Bachmann, Prose, and Schravin, who are extending this to a larger class of inequalities, so-called Stirling inequalities for the projectors, spectral projectors, and they do it for a nice class of potentials, like cutoff potentials, using the landscape function. And what I'm going to talk about, we're not going to use landscape function because we're not there yet, but it's the dream to combine what we're doing now with this to be able to handle rougher potentials. This is the tool that allows you to do that. But once again, you see here is this two constants, and my first aim is to try to get rid of these two constants, to have something that is better, not only in the limit. We know very well what are the asymptotics, right? We know the values law, we know what are asymptotics of this quantity. But we want to have it on the finite level. Given E, I want an estimate that looks like a good estimate for any energy, not only in the limit when energy goes to infinity, with the arrows that are not up to factor 10. This is the square potential. If your potential is like this one, infinite or finite square, well, we know what the eigenfunctions are. Think about direct eigenfunctions here, those sines or cosines. For the finite well, those functions will decay exponentially outside of this one. I'll have some pictures later, but it's just to say what my basic example is. What we're going to think about is how this eigenfunction is located in the phase space. And there are many ways to try to understand it. The one that we want to address, and we don't know how to do it, is to actually locate the Wigner distribution of this function. So with each function or signal in Rd, you have this object in R2d that is called Wigner quasi-probability distribution of the function. Have a nice way to compute it. You take your function, you take a shift of the function, multiply those, and take the Fourier transform. And this should be p, not pi. The nice properties of this Wigner transform is that when you integrate over momentum, you get the value of the function squared. When you integrate over the position with fixed momentum, you get the Fourier transform squared. The bad thing is that sometimes it's negative. It's not probability distribution. It would be very nice if it would be a probability distribution of your particle in the phase space. There are no functions other than Gaussians for which this is negative. But if you do the averaging in the right scale, you get something non-negative. In particular, if you take two functions and look at the integral of the product of the Wigner distributions, by the way, Wigner distributions are always real valued, you'll get something positive. It's tempting to take a Gaussian here. Then the Wigner distribution of a Gaussian is a Gaussian in R2d. If you take sin Gaussian, it will be sig in momentum. So it will be Gaussian that enjoys the uncertainty principle. Right? It will never be very good localized Gaussian both in addition momentum, but you can take any Gaussian and then this is positive. So if you can solve your function with a Gaussian, your Wigner distribution with a Gaussian, it's like looking at how much energy against Gaussian it has in different places. It's a nice positive function. Right. Hopefully I have some pictures. Yes. Those are the pictures. And it's a very naive one. So we have an eigenfunctions. These are infinite well, that is finite well. And we're looking at the Wigner distribution of those eigenfunctions. So we want to try to understand what is happening. So there are naive statement that I'll probably write on the blackboard that we're looking for and that we don't know how to get would be something like that. Suppose that I have an eigenfunction of energy E, and I want to look at its Wigner distribution and say take some allowed region in the phase space, either take it for a larger energy or take it for the right energy, but do some transformation of this one, take a little bit larger set, can we guarantee that this integral is positive? Quantitatively positive. The integral over the whole space is always equal to 1. It's non-negative, there are some cancellations, but you will see that most of the cancellations are inside the allowed region. So when you integrate over this, these cancellations will vanish. So we would want to say that there is some region here, so that if you integrate, you'll get hopefully a large portion of the energy of your eigenfunction should be concentrated in there. So it's what we're trying to understand. And you already see in this picture that there is some, I don't know if it's visible or not, but there is some non-negative thing that are happening near the end of the space. It's trying to go a bit up there and there. There is probably even better thing. We will have these regions on this, what I call ears, at the end of the allowed regions where we will see that, at least our methods say that we need to take a larger domain and it will be larger than the allowed one, especially here. And that's when we want to localize the function. There is another picture. This is absolute value of the Wigner, but the negative values are blue, positive values are red. You see that there are lots of cancellation in here, and there are two peaks in the Fourier space here and there. So there is no way to say that what is not around this energy shell is small. It's small only in average. But if you do the average in the nice sense, you hope that most of the energy is around this one. There is a work about Wigner distribution of eigenfunction, a very nice one. It's by Hanin, Zeldich, and one of the articles is with Zhu also, where they do lots of hard work and do very accurate asymptotic analysis of the Wigner transform of the eigenfunctions of harmonic oscillator, and moreover they have then a class of operators that are more general with potential that are convex and grow in quadratic form, where the limit, what you get is the same limits, same asymptotics as for the harmonic oscillator. Harmonic oscillator is a very nice operator. It's much nicer than anything else because of the symmetry between the position and momentum. We understand the exponential decay in special variable. By the symmetry, you have the same exponential decay in the second variable, and you never hope to have this decay in general. For example, the decay in momentum is 1 over polynomial. It's never exponential. There is not many examples where it could be this. But this Wigner distribution of eigenfunctions was studied, and in this regime of the asymptotic or semi-classical limit, things were done by those forces and some class of potentials. As I said, we don't know how to handle Wigner distribution in general, so we'll first look at a different interpretation of what is localization of phase space is, and usual idea in time frequency analysis is to think about your signal and see how much of the signal you have in different boxes. For example, by taking your function, think about a Gaussian, for example, take translates of this function and form a frame of these functions. Very roughly speaking, what I'm trying to do, I'm taking my phase space, cutting it into, in simplest way, squares, or equal rectangles, putting a bump into each of them, or Gaussian if you want symmetry in each of them, and try to, if you want, integrate the Wigner against this Gaussian and see what are the coefficients, how much of the energy I have in these places by comparing it to this. And there are ways to get frames from the translates. So I have special translates and then frequency translates and modulations of the same function. You can make frames of those. But what is more important, when we want not to have some estimate that will not lose a constant, we want not a frame, we want what is called tight frame. We want the energy to be equal to some of these coefficients. And there are Gabor tight frames as well. We'll know how to construct those. So you can construct a sequence of translates of one function, even with critical density, such that what you'll get will be a tight frame. We will not do that. We will do a very cheap construction of a tight frame that is better for our purposes. And it's elementary. So you take a partition of unity into positive bumps. I want each function to have a compact support in some cube. Then I know that the L2 norm is equal to sum of the integrals against those functions. But here each function is a function with compact support. So I can write the L2 norm as sum of the Fourier coefficients. So I take a bump, and then I take all the modulations here, and I get a tight frame just by this very elementary computation. It looks like I oversample. I have too many boxes. My boxes, they are intersecting in this variable, and they're quite small. I mean, for this function, I can choose this box, but I can also choose a larger box. Maybe I'm taking too much frequencies. But you will see that I have this normalization. At the end, I'm not going to count the number of boxes. I'm going to count the weight of these boxes. And the weight will be the integral of this function over the box. So what I'm having is I have some partition of unity into the phase space. And I'm going to count the number of places where I see the eigenfunction in this space. And since it's a tight frame, it will allow me to lose much in the multiplicative constant there. So now the bad part. And this is not so bad part yet. Right, so what I'm doing, this thing for each box, I have a function that lives there, and I want to compute the energy of this function according to my potential energy. So if you think about the energy of this function, what is it? It's h applied to the function, again the function, normalized by the L2 norm. When you compute this part, there are two things that happen. There is Laplacian, that is the square of the gradient, and there is potential part. The potential part is the same for any modulation. When you multiply by something of absolute value 1, the potential is the same. So for the potential part, we'll have the same here. For the kinetic part, the two terms, you see that they don't interact. One that corresponds to the gradient of the initial function, and it will be here in this energy. And the other one that corresponds to the gradient of the exponential function, it will give you the fixed term that it can compute. So the energy of these bumps, it grows quadratically in k in very simple way. And the energy of the initial rectangle or initial bump here is sum of the kinetic energy and potential energy. This is the kinetic one, this is the potential one. this is the one that I missed slide, and this is where we need, for the moment, that our potential is nice, and it's what we're trying to fight against. For the moment, we need the potential to be positive with doubling property and some reverse Holder inequality, because we want to find a partition of unity that satisfies these three properties. This partition should be concentrated in boxes. Each function should behave nicely as you want from a bound function. Its maximum should be bounded away from 0, and the first and second derivatives should be bounded by the size of the box on the right problem. So you want nice bound functions. But you want this partition of unity to be adjusted to your potential in this way. So we want the oscillation of the potential over each box to be bounded by the kinetic energy. I wrote oscillation squared bounded by the kinetic energy squared. And for this construction, I don't think there is a way to do it for bad potentials, so we need to adjust our argument and probably introduce the landscape function to get rid of this assumption that V is nice. But it's happening. There is some difference between our choice of good boxes and the good boxes that we were assuming to choose first by learning things from Pfefferman. We don't want the potential energy to be comparable to the kinetic energy. We want the oscillation to be bound. So this is a different thing, and we have time probably I'll comment on that. For example, if you think about harmonic oscillator, your energy shell is very simple. It's here, right? This is the part of the energy where x squared plus p squared is bounded by v. If I'll convince myself to take boxes where potential energy is comparable to kinetic one, I will have to take very thin boxes. So my potential oscillates. My potential is large. It's quadratically large here, so I need very small boxes where potential is large. And you will see what I'm doing here. I will lose a lot by allowing such large boxes. Here I'm saying I don't want to have so small boxes to control the potential energy. I want to control the oscillation of the potential. And instead of size like this is 1 over square root of e here, I will allow myself to take 1 over e to 1 plus. That is much larger. And it will help me to hope for a nice arrow that is smaller than the main part if my potential is growing like that. So this is an important difference between what we're doing and what was done before. There's some not so nice notation here, but let me try to explain what is happening. So now we have this partition of the phase space. In each part of the phase space, we have this rectangle. They overlap, but don't think about it too much. We have two regions, and so we fix the energy level, and we fix we fix some constant L. I also have to say that in this part, when I do the complete composition, I don't know what the energy is. I'm giving the decomposition depending on the potential once. I'm not, and it's also another difference between this and what was done before. You don't cut into boxes depending on the energy. You cut once, and then given an energy, you just compare how many boxes with this, roughly speaking, with this energy you have on the So this is the forbidden region, where the ground energy of the box, the first one, is already larger than your E. This is a very forbidden region, where not only the energy, but both, but potential energy and kinetic energy of the ground box is larger than some, say, 10. So there will be some multiplicative thing here, but it will happen only in this forbidden region, and it will be a small part of the whole thing. So, what I'm trying to do, I'm trying to say now, give me the curve, and this was the allowed region, and the phase space, basically count the boxes that lie nearby. It's too naive to be true. I will have to go up and down huge generations and take a bit larger part, but I'm trying to say that some part of my eigenfunction should be here, in these boxes where the energy is comparable to it. So first I'm saying that there is some parts where my initial energy is larger than E, and there are some parts that initial energy is so large that definitely my eigenfunction doesn't see those. And then I'm saying that if those are bad forbidden boxes, that all boxes in the very forbidden regions are bad forbidden, and in the forbidden but not very bad forbidden boxes, if your energy is larger than E, it should be L times the sigma j to minus 2, then you also forbidden. And there are some forbidden boxes in the allowed region. What happens in the allowed region, you have some box where the energy is around E. You have to go up and down, or in high dimensions around it, like L generations, keep those and throw away all the rest. Those are inside, and those are that are there. So those are keeping, these are good boxes, these are bad boxes, and there are bad boxes out there. And the theorem is that if you now compute the sum of the squares of the coefficients of eigenfunctions against all bad boxes, it is bounded by a small constant. The total energy is 1. Here I can get constant that depends on my potential and some parameters there, divided by L. L is something I'm choosing. So this is part of the, I mean, most part of the energy in terms of these coefficients, we know that sum of the coefficients is equal to 1 because it's a tight frame, and the most in the allowed region. That is, roughly speaking, this one, but I promise to tell you more. When I'm here, my ground energy is around E, and in many situations it means that I'm taking a larger box. When I'm taking L of those, I have this ears. For example, for the harmonic oscillator, the situation that I'll have here, the boxes are like that, so I will have actually the shell like that. It's reasonably seen here in the middle, but when I'm going to the ends of my curve in the physical space, I will take more of these boxes and they'll have the ears coming, where I cannot exclude that my eigenfunction is not living in some neighborhood of these points where this is small, but it is large. So this was the first result, and the second one is about integrated density of state, the count of the eigenvalues that are less than E, and what we have is the good boxes inside from one end, and the good boxes outside. The bad boxes inside. This is what is inside this shell from one side, and then all the good boxes plus those on the other. So this is the coefficient that we are losing. It's 1 plus 1 over, or constant over L. We can make it close to 1. And there are examples where the potential is, for example, polynomial or like that, where we know that the ratio of those is small. Not only limit, but for reasonable E, the ratio of those is small. One of the reasons to do this forbidden region was that with this property, after we take care of this one, we have a reasonable estimate for the ground state, where the first eigenvalue is. That is comparable to what was known before. But sure, this is not very good for when you have one function. You don't have to count this one with very good precision, but you have reasonably many of those. This is a good precision. And as I said, there are more questions than answers here. We don't like this class of potentials, yet we want to have more than very good potentials. And the game is to include potentials with high probability at the end. And one of my personal goals is to understand not only small paper, part of the paper by Hefferman, but the whole thing. And Hefferman found uncertainty principle that is a very beautiful thing there that allows you to work with specific differential operators. But yeah. Thank you very much for your attention.
Are there questions or comments?
Is the Coulomb potential allowed in the
Not directly. We didn't try to write this example, but it's very reasonable thing to do. I mean, a priori I need more than that, but I think it should be.
If you plug in a coupling constant lambda in the potential and take lambda to infinity, then things like you mentioned, like the Lipschitz-Rosenblum, or maybe Lipschitz inequalities about either the number of eigenvalues of the traces or so on, well, then they become asymptotic.
Yeah.
But this phase space localization can yield something that of how to approach this asymptotic behavior.
Yeah. There are some. This is a very good question, and there are some very nice examples in the original work of Hefferman where he says, "Yeah, sure, we know asymptotic behavior, but for example, if instead of harmonic oscillator, you take a potential that is x squared plus epsilon squared y squared. So you have two variables, and your harmonic oscillator is not isotropic, the potential now. Then the estimate that are there start working only for very large eigenvalues, because with small epsilon you don't have instruments to catch. So we're trying to have inequalities that will be there for all levels, right? Not only for very large energies as asymptotic results, but have estimates from above and below for a fixed E and potential and see what is your error in terms of potential. But yeah, there is no way we are trying to improve Buzz law or try to get the right constant and the error term there. Yeah.
A couple of times you have mentioned the problems associated with the fact that the Wigner function is negative somewhere, and you have tried to solve it different ways. I come from the field of quantum chaos, and there we solve it by using the Husimi function, which I'm well aware that has other problems. You don't like that solution? We
don't have tools to work with it. Probably it's a good alternative. Again, we looked a little bit at it, but we were not able to come by what we know how to do for the moment.
Okay, no, that's probably associated with the fact that it has other problems. And the second question is, you know, people in my field, like Heller or your co-creator, Bo Molly, has studied the problem, not in eigenfunction, but in groups of eigenfunctions, which makes the problem much easier, because there the localization is in classical structure, like periodic orbit and things like that. So you don't consider do that in the future?
We will have to talk more about it. I don't know exactly what you refer to. So we know that instead of thinking about one eigenfunction that is a bit naive, you should look at the spectral projectors, where you want to weigh those projectors in a nice way, and then you have some better control on nesting. Sure.
So that position will include like a window in the spectrum?
Yeah.
Okay, then this is what I meant.
We know that probably we can do it, and probably we can also weight it with some nice weight, then we have a better control of what is.
It seems an easier problem to
Yes, it's usually an easier problem to do, especially if you don't cut the spectrum very roughly, but do it in more smooth way.
David?
Yes, my question is kind of related to the first one by Timo. When you compute the Gabor coefficients with respect to your tight frame, so these are essentially discretization in view of the study of the linear distribution that you showed us. These are discretization of the convolution of the Wigner distribution of the eigenfunction with the Wigner distribution of the mother of the generator of the Gabor frames. So my question was, isn't that since you're not choosing a Gaussian, that is should be the most localized state for the phase space distribution, isn't that you get a more in the last estimates? Isn't that yes? But involving your last estimates on bad and good cubes, don't you get more non-zero coefficients if you choose because
I mean,
you get better estimates. The question is counterintuitive to me why you get better estimates with a compactly supported mother wavelet instead of a Gaussian.
First of all, to be clear, this was an example. We don't do Gabor, right? Because we can do Gabor only for very, very, very good bounded potentials where you control lots of things. In general, we want to construct something like this, the tight frame that has these properties, that is adjusted to our potential. We started with Gaussians. With Gaussians, we started to see if we can do it. We can do something with as well. Gaussians are nicer because you know that their wavelet transform. Their Wigner distribution is positive, and at the end you actually integrate your Wigner against some weight, and so the weight integrals. But this is a play that game that we're playing. With Gaussians, we can handle some nice potentials. If we want to go to potentials that are rougher, it looks like we want to do the cutoff with complex support. I don't know what is the right tool, right? We're working at this project. Sometimes we try to convince ourselves Gaussians is the things to go, but then on the technical side, it's easier to do if we don't want to have this multiplicative arrow to do with this kind of tight frame. Even I agree that Gaussians are the first thing you want to try. Even probably not the Gabor of Gaussians, but adjust the Gaussians to your potential in the right scale, and then take a frame of that. But I don't know how to construct a tight frame for Gaussians. We convince ourselves that it's not possible. If you just do Gaussians, try to adjust them and try to construct the modulation. Gaussian, so the nice functions to construct the type. But there are some functions where you can do tight Gabor frames.
I see. Okay, thanks.
Are there any more questions or comments? If not, then let's thank Eugenia again.
Tanto, darle cuenta a esa de